What's up guys? So today I'm going to be doing this problem 1510 stone game 4. uh, Alice and Bob takes turns into playing a game with Alice starting first. Initially there are n stones in a pile. On each player's turns, that player makes a move consisting of removing any non-zero square numbers of stones in the piles. So basically there are n piles and a number of stones in a pile, and that n is constant, and then Alice and Bob takes turn removing a square number of stones from the pile. So they can either remove 1 or 4 or 9. So that many numbers they can remove, which are square numbers. And at the end, whichever player cannot remove any stone, or whichever player removes the last stone, wins, and the next person loses. So both of them are going to play optimally. How do we solve this problem? Given a number n, how do we know that uh, whether Alice wins this game or not, right? So how do you solve this problem? Let's say we have one stone, and it's always Alice's turn first. So obviously he's gonna remove the first stone. So there is zero stones, so he wins. So if there are two stones, Alice can remove only one stone because one is a square number. So remaining one stone is removed by Bob. So Alice has nothing to remove, so he loses. 4 is a square number, so Alice can remove all the four numbers, so he wins. And 7, uh, let's say Alice removes one number, 1, which is a square number, then the remaining stones are 6. So Bob can remove 4 stones from that, so the remaining stone is 3, right? So on 3, Alice can remove the one number, Boss removes 1, uh, something like that. Okay, let's see. Why does Alice lose here? If Alice starts removing 4 stones, Bob will remove one stone, then Alice should remove only one stone, and finally Bob removes the last one stone. So Bob always, if Bob plays optimally, he can remove the last stone. So Alice loses in this scenario. If Alice starts removing one stone, Bob will remove 4 stones. Alice only can remove one stone, and finally Bob removes the last one. So either way, Bob removes the last stone, so Bob wins in this scenario. So let's say yarn is too high, 700, 800. I mean, there is some limit over here. How do we determine which player wins the game? This is a challenging problem because you have to go on trying all the combinations. So for example, let's say n is 26, right? So the lowest square number is 25. So all the square from 1 to 25 uh, are the possible numbers that Alice can remove, and Bob and the game starts continuing from the remaining number of stones between Bob and Alice, where Bob has the turn, right? So one way we can solve this problem is we can go on trying to remove uh, one, two square number less than n, right? Any of these numbers can be removed by Alice, and then we can do a game between uh, n minus the number removed, right? And if in this game Bob is the winner, that means in the previous game with n numbers, Alice is the loser. If this game Bob cannot win, that means in this game Alice wins. So yeah, let's start solving the problem that way. So we know that if yan won, obviously we know that uh, Alice wins, so just return true. If yan 2, we know that Bob wins, so we can return false directly. I mean, you can just stop at 1, but yeah, I like to do 2. How do we do this? So the number, we have to find the maximum number, square number, that is less than n. So for that we can do int Before that, let's just write a find function and return it, and we assume that the find function finds the optimum result that we are searching for. So n. Okay, so this is recursive function, and then it returns boolean n. And let's remove this logic here because this is where it needs it. Alright, so now let's find the square root of n. So square of this value would be the maximum square number that can be removed. So for I equals to square root, I is greater than equals to 1, I minus minus, and then we have to sort every combination. By removing every combination, we have to see whether Bob loses or not, and that's how we determine Alice wins or not. So remaining numbers is equal to n minus I into I. If Alice choose to remove I into I numbers, the current player choose to remove I into I numbers, then this is the remaining number. And then if we have to play remaining number, if so Bob's turn, so if Bob cannot win in the remaining number, that means Alice wins, right? So what we can do is basically we can return true. If none of these combinations Alice wins the game, then we can return false. So this is, yeah, this should give us the solution. 2, obviously it will give us the solution. It's hard coded. What about 3? True. 4. 5. So yeah, this is the solution, but then as you can see, this might be too the order of this function is higher because we are doing the sorts again and again. We're going down the tree and then again trying the next number, but so let's say the number is very high, let's say 1000. So we start with the maximum amount we remove, and then we go on down the tree and then recompute some of the values again and again. So we can remove that if we just do before that, let me run this problem so that we know that it's taking too long. Yeah, time limit exceeded as expected. Boolean dp, and then what we can do is dp equals to new boolean n plus 1, which will help us remember whether we have already calculated that value or not. If dp n is not equals to null, return dp n. Alright, and then we have to memorize this as well. So dp n equals to false, and here what we can do is return dp n equals to true. Right, it still works, and then let's submit this. Yeah, it takes 4 milliseconds and it beats 90% of the solutions. So this is the approach that I used for solving most of the problems, where I just write a recursive function and then do a solution, and finally that solution is not optimized, so I use some kind of memorization to make it efficient. Thank you guys for watching. See you guys next time.